Jai Hind to all. Today I am here to present one of the video lectures, that is lecture number 3 of subject Signal System BEC 403. The topic is Signal Transform. I am Dr. Amit Garg, Associate Professor in EC Department of Akgec. Let us start the video. Okay. So first of all, Fourier transform representation. Okay. So Fourier transform basically is a mathematical tool which basically changes a time domain signal into a frequency domain signal and vice versa. Means if we will apply the Fourier transform on a signal, then we will get the frequency content of the signal, and if we are having frequency information and we will apply the inverse Fourier transform, then we will get the time information. So this is used for the analysis of aperiodic signals and some of the periodic signals. For periodic signals, we will use this Fourier transform, and some of the periodic signals for which Fourier series representation cannot be possible, for those cases we will apply the Fourier transform for finding out the frequency information. Okay. So why frequency domain representation? So what is the requirement of frequency domain representation when we are having time domain representation of signals with us? So allow us to observe several characteristics of the signal. So frequency domain basically allows us to observe several characteristics of the signal that are either not visible or not easy to see in the time domain. Means when we will apply Fourier transform over the signal, we will get the frequency information and basically some of the informations that are not visible in time domain can be easily seen in frequency domain. Like an example, cyclic behavior of signals can be seen in better manner in frequency domain as compared to time domain. In frequency domain, we can see cyclic behavior in a better manner as compared to the time domain. Okay, so in this lecture, we will discuss various types of signal transforms like continuous time Fourier transform, discrete time Fourier transform, discrete Fourier transform, Laplace transform, jet transform, and then mainly we will discuss CTFT, DTFT and DFT in this lecture. All these transforms are used for the analysis of aperiodic signals or for periodic signals for which Fourier series representation is not possible. Okay, so let us start with the continuous time Fourier transform. So basically, continuous time Fourier transform or CTFT specifies the spectral content of a signal, thus providing a frequency domain description of the signal. Okay. So here in this case, in continuous time Fourier transform, the signal that we will take is continuous time signal, and let us suppose the signal is xt. So condition is that it must be continuous and aperiodic. Then we will apply continuous time Fourier transform over the signal, and after applying this continuous time Fourier transform over the signal, we are having the transform that can be represented by x j omega, that is again continuous and aperiodic. Okay. So here we can see any aperiodic signal can be represented as a linear combination of complex exponentials which are infinitesimally close in frequency. So the representation takes the form of integral rather than a sum. This is why we are getting the continuous signal. In the Fourier series representation, as the period becomes infinite, the frequency components form a continuum and the Fourier series becomes an integral. Means why we are using integration sign here. If you will see the expression, this is the expression of x j omega or the Fourier transform. We can see here in this expression, this is the signal xt, and we are multiplying by an exponential e to the power minus j omega t and integrating from minus infinity to infinity. So this is the Fourier transform. And if we want to again obtain the signal xt from this x j omega, then we will use the expression 1 upon 2 pi minus pi to pi x j omega e to the power j omega t d omega. So here we can see this is the definition for inverse Fourier transform. So here comes like why we have used the integration sign. So integration sign is used because when we have used Fourier series representation, in that case, if the period becomes infinite, the frequency components form a continuum. Means when as the period becomes infinite, then you can say in frequency it will become almost 0. So that you can say the components are arranged together by a separation of almost 0. So that's why this summation sign will become converted into integration here in case of Fourier transform. Okay. So this xj omega is nothing but xj omega or x omega is the spectrum of xt, and it is a continuous function defined for all values of omega. So you can see this is continuous with respect to omega. So if you will change the omega from minus infinity to infinity, the spectrum will continue changing. So therefore, an aperiodic signal has a continuous spectrum rather than a line spectrum, which was in the case of Fourier series representation, where xt and x omega are Fourier transform pair, and this can be represented like this: x omega will become Fourier transform of xt, or you can also write it xt equals to Fourier transform of Fourier inverse of x omega, and this is the Fourier transform pair xt is x omega. Now we will see this x omega is nothing but continuous, it is a complex function of variable omega. So for analysis of complex function, we will use magnitude and phase. So this x omega can be written as xr omega plus jxi omega, and we can also write it in polar form, mod of x omega e to the power j angle x omega, where mod of x omega is nothing but real part square plus imaginary part square. So under root xr square omega plus xi square omega, and if you calculate the angle x omega will become tan inverse imaginary part upon real part is the angle or x omega. Okay. Now we will see some problem based on continuous time Fourier transform. Let us suppose we are having a signal xt equals to e to the power minus at ut, where a is a constant which is given greater than 0. Now we have to obtain the continuous time Fourier transform and draw the frequency spectrum. So now if you will see the frequency spectrum, basically frequency spectrum, this is a plot. So this plot consists of two plots. One is magnitude plot, another one is phase plot. Magnitude plot and phase plot. So this magnitude plot is a plot between magnitude of x omega with respect to omega versus omega, and this phase plot is a plot between angle of x omega versus omega. So this frequency spectrum plot is a plot combination of these two plots. Okay, so whenever this frequency spectrum is asked, it means magnitude plot and phase plot. So this is the case. These two plots we have to calculate, we have to check when the frequency spectrum is basically a complex quantity. Okay, and if it is an real quantity, then there is no need to plot this phase plot. Okay, so here we can see this how we will calculate the CTFT and how we will draw the frequency spectrum. So this is the expression that we have seen for Fourier transform: xj omega equals to 0 to infinity e to the power minus at e to the power minus j omega t dt. Okay, so you can see this how we have obtained. So you know the formula: minus infinity to infinity xt into e to the power minus j omega t dt. This you can as minus infinity to infinity. Xt is given as e to the power minus at ut into e to the power minus j omega t dt. Now this ut will make the integration sign from 0 to infinity. So that's why we have written here xj omega will become 0 to infinity e to the power minus at e to the power minus j omega t dt, where limit of integration is put from 0 to infinity, and we will simply solve it. When we have solved it, so we have obtained the value 1 upon a plus j omega. So the Fourier transform of xt equals to e to the power minus at ut is 1 upon a plus j omega, and here a is greater than 0. Now you can see xj omega is basically a complex quantity. So for analysis purpose, what we will do, we will draw the magnitude plot as well as the phase plot. So you know xj omega is complex here. So first of all we will calculate the magnitude of xj omega. So magnitude of xj omega is under root of real part ka square upon under root of real part ka square plus imaginary part ka square, imaginary part square in both numerator and denominator. So in numerator it will become 1 and in denominator it will become under root a square plus omega square. And if you will see the angle for phase plot, this will become angle of x j omega will become minus tan inverse omega by a, because the angle will become tan inverse 1, which is 0, minus tan inverse tan inverse omega by a. So this will become minus tan inverse omega by a. Now we will plot. How we will plot? We will take some values of omega and corresponding we will calculate the value of magnitude of x j omega. Okay, like if you want to see the value here, let us suppose at omega equals to 0, so we can see the value will become 1 by a. So we are having this value. Okay, now if we are checking the value at plus minus a, so if you will calculate the value of plus minus a, then it will become 1 by root 2 times a. So you can see this value is 1 by root 2. You can also write it 1 by root 2 times a. Okay. And similarly, if you will increase the value up to infinity, so this value will become 0. Okay. So you can see this plot is tending towards infinity in both directions. Okay. So this is the magnitude plot. So you can get the maximum value of magnitude at omega equals to 0, where a is greater than 0. And here the phase plot, you will see at omega equals to 0, this will become minus tan inverse 0, it means 0. So you are having this angle value. At omega equals to a, you will find at, if you will see here, at omega equals to 0, this will become 0. At omega equals to a, this will become minus tan inverse 1, which it means minus 45 degree, it means minus pi by 4. So at a, it will become minus pi by 4. At minus a, it will become pi by 4. And if you will see at at omega equals to infinity, okay, so this will become minus tan inverse infinity, and it means minus pi by 2. So it is minus pi by 2, and for minus infinity it will become plus pi by 2. So you are having this type of plot, which is the phase plot. So this is how we can obtain the magnitude and phase plot for continuous time Fourier transform. Now again we are having another type of problem, xt equals to e to the power minus mod t. You know mod t equals to t for t greater than 0 and minus t for t less than 0. Okay. So this can be written like, first of all we will write the definition. According to the definition, xt into e to the power minus j omega t dt. Now according to this, we will divide the limit from minus infinity to 0 and 0 to infinity. So between minus infinity to 0, this will become minus t. So this will become e to the power at, and between 0 to infinity it is plus t. So it is e to the power minus at into e to the power minus j omega t dt. Okay. So now we will solve this. So this is 1 upon a minus j omega, and this is 1 upon a plus j omega. So we can see here the value is, after solving, 2a upon a square plus omega square. So we can see here x j omega is real. So x j omega is real. This is the signal we have drawn. So you can see here we have only obtained the magnitude plot. So here the only magnitude plot is there. When you will put the value of omega equals to 0, okay. So in this case there is no need to plot only magnitude plot. You can plot the magnitude plot or only or the combined plot. Okay. So this is the combined plot. So we are not plotting here the angle magnitude of x j omega. We are simply plotting the x j omega. So this is the plot. Okay. Now another problem. Find out the inverse Fourier transform of x omega equals to delta omega minus omega naught. So here we will use the definition of inverse continuous time Fourier transform. So this xt equals to Fourier inverse of x omega. So x omega is delta omega minus omega naught. So you know, so we will write 1 upon 2 pi minus infinity to infinity x omega into e to the power j omega t d omega. Now x omega is delta omega minus omega naught. So we will put it over here. Now this impulse is only defined at omega equals to omega naught. So we will write 1 upon 2 pi, this value at omega equals to omega naught. So we are having this 1 upon 2 pi e to the power j omega naught t. Now we will, so it means Fourier inverse of this is 1 upon 2 pi e to the power j omega naught t. So delta omega minus n omega naught is Fourier transform of 1 upon 2 pi e to the power j omega naught t. So with this you can write like Fourier transform of 1 upon 2 pi e to the power j omega naught t is these are the Fourier transform pair. So 1 upon 2 pi e to the power j omega naught t will become delta omega minus omega naught. So from here we are having two important results, that the Fourier transform of e to the power j omega naught t is 2 pi delta omega minus omega naught, and Fourier transform of e to the power minus j omega naught t is 2 pi delta omega plus omega naught. So these are the important results that we can use later on in the various problems. Like one problem is find out the Fourier transform of xt equals to cos omega naught t. So xt equals to cos omega naught t is e to the power j omega naught t plus e to the power minus j omega naught t by 2. We can write cos omega naught t as e to the power j omega naught t plus e to the power minus j omega naught t divided by 2. Now x omega will be Fourier transform of xt. Xt is this. Now we can separate it like 1 by 2 Fourier transform e to the power j omega naught t plus 1 by 2 Fourier transform e to the power minus j omega naught t. Now Fourier transform e to the power j omega naught t is 2 pi delta omega minus omega naught. We have already calculated it. And Fourier transform e to the power minus j omega naught t dt is 2 pi delta omega plus omega naught. So we will put these values over here. So the Fourier transform of cos omega naught t will comes out pi times delta omega minus omega naught plus delta omega plus omega naught. Okay. So we are having the Fourier transform of cos omega naught 2, which is like this. Okay. So you can see if we will draw this Fourier transform, so we can see this x omega will become minus, there are two impulses located at omega equals to omega naught and omega equals to minus omega naught, and the magnitude is pi. So this is the Fourier transform of x omega. Now the Fourier transform of xt equals to sin omega naught t. Again, using Euler's formula, we can convert this sin omega naught t as 1 by 2j e to the power j omega naught t minus e to the power minus j omega naught t. So we have written xt like this, and we have separated it out, and then take the Fourier transform of e to the power j omega naught t, which is nothing by 2 pi delta omega minus omega naught, and Fourier transform e to the power minus j omega naught 2 pi delta omega plus omega naught. So from here we will obtain the result pi by j delta omega minus omega naught minus delta omega plus omega naught. So Fourier transform of sin omega naught t is comes out to be this. So here we can see this impulse is located at pi by j, and here it is from minus pi by j. Okay. So again there are two impulses located at omega equals to omega naught and omega equals to minus omega naught with magnitude as pi by j and minus pi by j. So this is how we have calculated the Fourier transform of xt equals to sin omega naught t. Now find the Fourier transform of the signum function xt equals to signum of t. So you know signum function is signum of t is 1 for t greater than 0, minus 1 for t less than 0, and 0 for t equals to 0. So signum function can be rewritten as, signum function we can easily write it like signum of t is ut minus u of minus t, ut minus u of minus t. So this can also be expressed like this. But we can see this function is not absolutely integrable. So we approach this problem by considering signum t to be a sum of exponential. So we can write this signum function as e to the power minus at ut minus e to the power at u of minus t in the limit as a tends to 0. So if we'll put limit a tends to 0, then we can write this function like this. Okay. Like you can also see, this is the signum function, and this is the function that we have assumed, and if you will put the limit a tends to 0, so this is nothing but this function, this is nothing but this function. Okay. So that's why we have written like signum t is limit a tends to 0 e to the power minus at ut minus e to the power at u of minus t. Then we will take the Fourier transform on both sides. So Fourier transform e to the power minus at ut minus this. So Fourier transform e to the power minus at ut is 1 upon a plus j omega, e to the power at u of minus t is 1 upon a minus j omega, and after solving this we are having 2 upon j omega value. Okay. So this is the Fourier transform of signum function 2 upon j omega. Now here we will also see the magnitude and phase spectrum. So angle of or magnitude of x omega is 2 by omega, okay, and the phase spectrum is minus tan inverse omega by 0. So it will become minus pi by 2 and pi by 2 for omega greater than 0 and omega less than 0. So this is, you can see 2 by omega, it means for omega equals to 0, this value is infinity, you can say, and for omega tends to infinity, this value is comes out to be 0. And similarly the angle plot is like this, or the phase spectrum is like this. Now find the Fourier transform of the unit step function. So unit step function can be expressed as in the form of signum function. Okay, so 2ut can be written rise 1 plus signum t, or ut is half plus half of signum t. Then we will take the Fourier transform on both sides. So we are having Fourier transform 1 by 2 and Fourier transform 1 by 2 signum t. Okay, so this is comes Fourier transform of 1 and Fourier transform of signum t. And Fourier transform 1 is nothing but 2 pi delta omega, and Fourier transform of signum t we have already seen 2 by j omega. So we will put these values here. So u omega is pi delta omega plus 1 upon j omega. So ut is pi delta omega plus 1 upon j omega. Okay, so this is the Fourier transform unit step signal. Now comes out to be another transform, the discrete time Fourier transform, like CTFT is applicable for continuous time signals, DTFT is applicable for discrete time signals. Here we can see that xt is discrete, xt is written like xn, this case is discrete and aperiodic. This is the signal xn, and Fourier transform is represented by x e to the power j omega, which is again continuous and but periodic. Like if you see the CTFT, it is continuous, and aperiodic, it is periodic with period 2 pi. Okay, so after 2 pi it will get repeated itself. Okay, and important thing is that DTFT is applicable both for infinite and finite time duration sequences and periodic with period 2 pi. So if you will see the expression x e to the power j omega can be written as summation n equals to minus infinity to infinity xn into e to the power minus j omega, and this is the analysis equation. And if you want to find out the inverse, then you will take the xn equals to 1 upon 2 pi, because it is periodic with period 2 pi. That's why we are not putting any limit from minus infinity to infinity, but it is from minus pi to pi. Or you can also write it from 0 to 2 pi x e to the power j omega into e to the power j omega and d omega. And here, because the sequence is discrete, so in analysis equation we are using the summation sign with the limit summation n equals to minus infinity to infinity. If the sequence is of finite length, then there is no need to put the limit from minus infinity to infinity, but the limit is from as per the given sequence. Okay. Now find the discrete time Fourier transform of the sequence xn equals to 2, 1, 2. So we are having our finite duration sequence for which we have to find out the Fourier transform. So we will put x e to the power j omega is summation n equals to minus infinity to infinity xn into e to the power minus j omega n, because the sequence is starting from 0. So this is n equals to 0 to 2. So these are the values corresponding 0, 1, 2, and we are putting these values over here. And finally we are having 2 plus e to the power minus j omega plus 2 e to the power minus j omega. Then after manipulating it, we are having the result 1 plus 4 cos omega into e to the power minus j omega. So this is nothing but the DTFT of this sequence. Now another sequence is, we have to find out the Fourier transform of xn equals to un minus u of n minus n. So you can see this can be expressed as xn equals to 1 for n equals to 0 to n minus 1, because you are having a sequence which is like un, this is your sequence un starting from 1, and un minus n means there is another sequence which is starting from here with negative sign. Okay, so you are having so you know all these sequences get cancelled. Okay, so that's why you are having the sequences from 0 to n minus 1. So we are putting the limit from 0 to n minus 1 into e to the power minus j omega n, we can write it like e to the power minus j omega whole to the power n, and this is sum of n terms. So 1 minus r to the power n, r is common ratio, which is e to the power minus j omega. So you can write it like 1 minus e to the power minus j omega n upon 1 minus e to the power minus j omega. Then we have manipulated it. We have written it e to the power minus j omega n by 2 into e to the power minus j omega n by 2. Similarly, in denominator we have done this, and after solving it, we are getting the result e to the power minus j omega n minus 1 by 2 sin omega n by 2 upon sin omega by 2. Now, discrete Fourier transform, like in case of DTFT, we have seen that the spectrum is continuous, and it is again getting the spectrum is continuous between 0 to 2 pi. So again, it is having infinite values. So if we want to convert that infinite values into finite values, we have to sample the DTFT signal in frequency domain also, so that we are having the number of points at which we can find out the transform value. So this is DFT. So here we have omega, which is continuous previously. So we are writing omega equals to 2 pi k by n, and we are putting this into this equation, and DFT is only applicable for finite duration sequences. That's why we are putting the limit from 0 to n minus 1 summation. So this is the formula, so xn e to the power minus j 2 pi n k by n, and corresponding IDFT is this. We have to divide by 1 by n for normalizing it, and here we can see one question: compute the DFT of the sequence, sketch the magnitude and phase spectrum. So xk can be written like summation n equals to 0 to 3, because the sequence length is 3, xn e to the power minus j 2 pi nk by n. Now we will put this limit for each and every value of k. The n will vary from 0 to 3, and k itself will vary from 0 to 3. So for k equals to 0, k equals to 1 and k equals to 2, we have find out the value of x0, x1 and x2, where n is varying from 0 to 3. So we are having this value like similarly for this. So this is the xk, and if you want to plot the magnitude spectrum, then we can simply take the mod of it, and here we are getting the angle of it. So this is mod of xk and this is angle of xk. So these are the references. Thank you so much.